to present a talk. So essentially, my talk is somehow not related to the one that we heard before, but somehow not so far anyhow. So essentially, I want to present an exact solution for a quench problem, which is of the same type that you saw in the previous talk at the very end, but it doesn't has to do with the heat transport, but with particle transport, actually spin transport. So sorry, these are my my collaborators are from Oxford. One is Mario Collura, and the other one is Andrea De Luca. So the paper is on the archive, it's under review. So essentially, okay, I have not to probably introduce this, but let me just mention some, well, fix the notation. So what I want to discuss is a problem of dynamics, one-to-many body system. So you know this is a very complicated problem in general. If you want to know the wave function for many body system after certain time t, what you have to do is formally evolve with an Hamiltonian, and it's a very hard task. Numerically, it's feasible, but analytically, it's always very complicated, especially if the problem is interacting, if you have an interacting quantum system. So what I want to discuss now, actually, it's a prototype of non-equilibrium, let's say, device in which you have prepared your system at time 0. Experimentally, you can think to this. It's a one-dimensional system. At time 0, you prepare in 2 halves. So on the left, we have a certain state, which is psi left. And on the right of this one-dimensional system, we have another state, which is psi right. They can be pure state or density matrices, in principle. So density, if you think to density matrices, the most convenient way is probably to think about generalized Gibbs ensemble. So it might be that rho left is exponential of beta. Beta is inverse temperature times Hamiltonian minus mu times number of particles, mu is chemical potential. Depending on how many conserved charges you have in your system, beside energy and perhaps particles, you might build, of course, a generalized Gibbs ensemble. This is what people also do now. And it is especially useful when you think about thermalization in integrable system, which are a system which have an infinite number of conserved charges. And there, when you speak about thermalization, you have to do it in this context. It doesn't make really sense to speak about thermalization in an integrable system to a Gibbs ensemble, because you have many conserved charges. So this rho left and rho right, there will be this type of ensemble in general, or pure state. And what you want to understand is, well, actually, I have some initial state that time evolve it with a certain Hamiltonian. The Hamiltonian will couple the left and right part in general. There will be something happening for particle transport, heat transport, as we saw. But normally, you are interested in understanding the large time limit because this is easier, and if it is the case also, the large space-time limit, in which both x and t, they are large compared to the lattice spacing. Okay, so this is the setup. This was somehow, well, of course, it's a very physical question, especially if you have some system which is partitioned in 2 halves, understanding how, for example, energy will flow from the left to the right, or particle, they will spread from left to the right if you have some inhomogeneous initial state. But essentially, it was, well, for me, popularized by Bernard and Denis Bernard Benjamin Doyon in a paper of 2012 when they applied this to a gapless quantum system in 1D, which are special. Okay, so the model which I want to consider here, it's again, it's a sort of, I think you know this model, at least I hope so. It's a paradigmatic model in condensed matter, I would say. It's called XXZ spin chain. So you see, you have so the Hamiltonian which will drive the time evolution after the two couple, this left and right system is this one. So you see, you have well, essentially a flip term. You can flip the spin. So S is a spin 1/2, well, sigma over 2 if sigma is a Pauli matrix. So this term can flip the spin. So it can flip one spin down side I and then essentially move it toward the left or the right. So a sort of kinetic term for the spin. And this term is an interaction, is a sort of interaction which is of a ferromagnetic type between the Z, in the Z direction. Of course, this model you can fermionize. The first part is somehow the free fermionic open term, so it's the somehow trivial part, simple term. And the second term, it's an interaction of the type density-density. So you penalize if you have you feel you have two fermions, spin 1/2 fermions on neighboring sites. Okay, so the state which I want to consider is a very simple state, but nevertheless it's quite non-trivial, you will see. So it's a state in which on the left we prepare, for example, well, let's look at this one. This will be the main focus. So it's a state in which on the left all the spin they are up, and on the right they are down. So the left there is a kink. The initial state is a kink. All spin are up on the left and right and down on the right. So it's a simple state. So what can happen when you apply this Hamiltonian to this state? Well, you can have spin flip. And then you generate a transport of spin. Magnetization profile will change. Okay? At time equals 0 is a step function, the magnetization. And the time different from 0, it will be some function. Okay? Some non-trivial function. And the task is computing that function. Okay? Not only that function, but also the current, how much spin you transfer from the left to the right. Okay, of course, this state you can think in a more some generalized way as a density matrix in which on the left you have some finite magnetic field, positive. On the right you have some finite magnetic field, but negative. And you take the limit in which h goes to infinity. Okay? So also this problem is interesting. It's a problem in which the expectation values of the spin is not plus minus 1/2, but it's a hyperbolic tangent of h, where h is this and this positive. Okay, we can solve both the problem. But this is somehow more, it has an historical meaning. It's called domain wall initial state. Okay, so the reason why this problem is interesting is to analyze the spin transport in the XXZ spin chain. Well, it is a very old problem, actually, you will see. And it's because it was known since long that in the gapless phase, so the model is gapless if delta, which is this parameter, is in modulus less than 1. Okay, so in the gapless phase, the spin transport is ballistic. And this is quite remarkable because this model is interacting. And, well, it's integrable, but it's interacting. It's not a free model. There is not free fermion. And the spin current is not a conserved quantity. So you might ask you why the transport is ballistic. Why I have a persistent spin current in the system? And no, it's not diffusive. Of course, it's diffusive if delta is 0, but as soon as you add interaction, you can ask the question why it remains ballistic. If delta is larger than 1, the model is gapped. There is a gap, and there the transport is diffusive, becomes diffusive. You have pure diffusion. So there is a sort of phase transition, delta equal 1 in the transport. Spin transport is ballistic if delta is from -1 to 1, and if delta is larger than 1 or less than -1, it becomes diffusive. Ballistic, okay, you can, well, the standard definition of ballistic is you have, if you take linear response, you have a finite Drude weight. So in linear response theory, this is the way in which it was the term comes about. So you can compute the Kubo formula for the conductivity, and you see that there is a peak at omega equals 0, which means that essentially there is a persistent current. So the system, when you add a small magnetic gradient, magnetic field gradient, respond, producing a current which stay there. At time equal infinity, you see still the current in the system. So it's like a supercurrent. In this sense, ballistic. So it doesn't die. When delta is larger than 1, there is diffusion, which means that if you wait long enough and you are far from the contact point, you don't see anything. The current die. Okay, so that's... Yes, yes. Sure. It depends how you take the order of limit. If you take... if you take first the limit in which the system is infinite, and then the limit in which you wait long enough, you will see a current flowing. Yes, before then the limit in which t goes to infinity. Otherwise, you will have revival, for sure. There is no way. Yes. But the most interesting case is the case in which you don't have revival, because there you can see really this difference. Well, at least for me. Okay, so this was the motivation. So this is a first the MRG paper which analyzed the problem, just to again give some intuition. The paper is also a famous paper because this was really, I guess, one of the first papers in which it was applied the MRG to study time evolution. And they study time evolution exactly of this domain wall initial state in the XXZ spin chain. Exactly the same setup. So here you see a magnetization profile. Actually, it's the modulus of the magnetization. It's the modulus of SZ. And this plotted in a space-time diagram. So here you have X, or N, the number of sites. And here you have T, time. Okay? So time is the MRG1. So you see that there is this cone. So here is delta equals 0. This picture is delta equals 0, but it doesn't change that much up to delta equal 1, essentially, when the model is isotropic. So if delta is 0, there is this cone, and it means that outside this cone, the system has original values of the magnetization. So here, essentially, doesn't anything happen. There is no any current going. The current is flowing inside this cone, where the magnetization profile changes. So from left to right. So essentially, you see here. So on the left is 1/2. And on the right, it goes to -1/2 with a function that I will compute for you. I will compute it in general. This is delta equals 0 is easy. It's in the next slide. Okay, so this is the function that is actually correspond to a light here. A slice of this cone, which is a light cone, because the excitation has a maximum velocity, which builds this light cone. So here, so also this is a signature that the transport is ballistic, because everything actually depends on x over t. This profile is a scaling function of x and t, as you will see. So there is this symmetry in x and t, which is a signature also of ballistic transport. Here, the case is delta equal 1. The color code is different. So you see that also inside this cone, essentially, you don't change that much from the expectation value of modulus equal to 1/2 of the magnetization. And what happens actually is this cone is closing. And the region where the profile of magnetization switches from -1/2 to 1/2, it keeps to be a step function, essentially, if delta is equal to 1. So in this paper, they also conjecture a form, is numerics, for the magnetization profile, which is this function, magnetization profile. If you take x larger to respect to the lattice space and you wait long enough, the system has to be infinite, otherwise this limit doesn't make sense. So essentially what they conjecture is that the magnetization profile becomes a scaling function of x over t to the alpha, and this exponent alpha depends on the interaction delta. So if delta is 0, alpha is 1. So the free fermion model, this profile is a function of x over t, which also is telling you that there is this ballistic transport because you can rescale x and t the same way. If delta is 1, so you are at this, in this case. So diffusion will be alpha equal 1 half, right? So if delta is 1, they conjecture actually super diffusion. This was the conjecture with alpha at 0.6 from the best fit that they have for this data. So I will tell you what actually we can say about this number. So they conjecture actually super diffusion at delta equal 1 and let's say in a way ballistic transport in the other cases. So this problem was reconsidered also by Prosen and his collaborator recently. The paper is published in Nature. Don't ask me why, because I found very close to this one, but anyway. So essentially, so what they do is to take as an initial state this state, which is very similar to, well, essentially is the one that I will consider. You have some finite magnetic field. If you take mu going to probably 1, I guess, you have the domain wall initial state, because that becomes a projector. Okay, so that's the domain wall initial state. And they study numerically, again, transport of spin transport in the XXZ spin chain with this model. Well, actually, with this initial state. And they claim, so this is numeric, there is numerics, so there is no analytical support, but it's numerics. It's, of course, professional numerics. So what they claim is that the transport is a spin transport for, let's consider mu equal 1, which is this domain wall initial state. So the spin transport is ballistic up to delta equal 1. At delta equal 1 is super diffusive. The exponent that they claim is 0.6 again, so it's the same as here. They confirm this result essentially for super diffusion at delta equal 1. And it becomes diffusive for delta larger than 1. So that's the essentially the background about this problem. So yes, so the h equal to infinity limit, which is the domain wall initial state, it seems singular because apparently there is some singularity in mu. This is again numeric. So it means that if mu is finite, you have a finite magnetic field, this super diffusion exponent seems to be 2/3. But as soon as you take this limit in which it goes to infinity, you fully polarize the initial state, it seems that the super diffusion exponent goes down to 3/5, or 0.6. But never mind, so think about only to the domain wall initial state. Okay, so let me tell you how you solve this problem for the free fermion, so delta equals 0, which is an interesting point. It's a legitimate point to study because it's a representative point for the in the gapless phase. So delta equals 0, the model XXZ is free fermionic. It's a very simple tight binding free fermion Hamiltonian. And the initial state is a state in which you have one fermion per lattice sides on the left and no fermion on the right. Okay? So you can solve this problem exactly. It's not difficult. You have to, if you want to work out the current, the magnetization profile, you have to do a stationary phase analysis of the correlation function, which of course I will not do it, but there is a simple interpretation of the result, which is very nice, and it boils down to a, well, essentially hydrodynamical interpretation. So the interpretation of the problem is like this. So it comes from the exact solution. So essentially, what you can do is to think at t equal, you think it's semi-classically in this px plane. So p is the momentum, the single particle momentum. X is the spatial coordinate. So if you take time 0, so what happens is that you feel all the single particle energy levels in the first Brillouin zone on the left, from minus pi to pi for this tight binding model. And then on the right you have nothing, because you have no fermion, you have no any state, you have no particle that can you can adjust in the single particle energy level. Then you time evolve this initial distribution, and what happens is just that well, the fermion, which has a certain momenta p, will move with a certain velocity, which is the group velocity, with the phase velocity. V of p, no, the group velocity is sine p, following from the Hamiltonian, the derivative of the dispersion with respect to the momentum. And so it means that after a certain time t, the fermion, which has velocity v of p, will move, and it will be at position t times sine p. Okay? So if you want to know what is the distribution of fermions at a certain position x, well, what you have just to, after a time t, well, what you have just to do is integrate over all the fermions which have velocity larger than x over t, because they are the ones that came there after a certain. This follows from the exact solution, but it's a very simple interpretation. It has a very simple interpretation. So essentially, you have this initial distribution of fermions, and it gets modified in a very simple way. Just the single particle, they will move with their group velocity, and then you integrate over the density, over the momenta which are occupied, and you get simply the distribution of the fermion, which is trivially related to the distribution of the spin, well, the total profile of the magnetization. And it turns out that rho is arccosine of x over t. So that function, which was in the first one of the first slide, was arccosine actually of x over t. Okay, so that's so here there is an interesting remark which I don't know if it might be interesting for you. It's a mathematical remark in a way. So if you take zeta equal 1, so you are looking at the boundary of the light cone. So essentially you have always to take in mind this picture. So you have something which happens only inside this cone. So this is x over t equal to minus 1, and this is x over t equal 1. And now you want to understand what happens actually when you cross a region where there is something, there is a current, and a region where there is not. So you look at the limit of zeta going to 1 here. Zeta is x over t. And you see that there is a square root singularity. So actually this profile is steep. It is something like this. But here it's 90 degrees, because there is this square root singularity. So this square root singularity means, if you know this a bit the story, that you can actually get a better approximation for the density, which is not this arccosine, very close to the boundary here, when it crosses from something which is different from 0 to 0, because you cross this line. And the density has this form with an Airy function. Big X is x minus t over t to the 1/3, which is related to Tracy-Widom distribution. If you know, the Tracy-Widom distribution appears in many contexts, especially in random matrix, as the statistic of the largest eigenvalue of an Hermitian random matrix. Here it appears in the density near the edge in a free fermionic system. So you see this oscillation, this nice oscillation here are related to this Airy function. And this is what happens when you cross the boundary of the light cone. All right, so this is the free fermionic problem. So let me tell you briefly what to do when the problem is interacting, because there is a step. Well, actually, there are more than one step of difficulty that you have to climb to solve the problem when you have interaction. So the idea is that, and it was put forward 1 year ago, essentially, more or less. So the idea is that forget about solving the problem exactly on the lattice, because this is impossible. This is absolutely not feasible. It's too complicated. You have to do Bethe Ansatz, but even more. So you have to somehow forget about this. But what you can do is somehow try to generalize this hydrodynamical argument that I did for free fermion to the interacting case. So that's the idea. So the basic assumption of hydrodynamics is that if you have an inhomogeneous system like this in the space-time diagram, there are regions which are macroscopically big, but they are smaller compared to the system in itself, where you achieve local thermalization. So here you can think to have some stationary distribution of, for example, quasi-particle occupation numbers, like in the case of free fermion, like on the slides that I showed. Okay, this will depend on x and t from the position where you are. And what you have to understand, so here you can still describe your quantum system as an equilibrium with a space-time dependent potential, it's a Lagrange multiplier essentially. So what you have to understand is how conserved charges, like for example in the free fermionic model occupation number, they move in the space-time diagram. Okay? And they should move in order to satisfy conservation law of all the conserved charges that you have in your model. So for example, energy, particle number, if you have more conserved charges, you have to write more equation of this type. So what you have to, so what you do in an hydrodynamic picture is to trade the complicancy of solving exactly the model on the lattice with solving continuity equation, which tells you how the conserved charges moves when you essentially try to explore the space-time. Okay? But in order to be useful, this equation, what you have to, this conserved, let's say, continuity equation, what you have to know is how we express the conserved current in terms of the charge. Because otherwise, this is useless. If you know how J it is expressed in terms of Q, then this is an equation really for Q that with some boundary condition you can solve and you can ask what happens. Okay, this has a long history. It goes under the name of macroscopic fluctuation theory, and it was especially applied to this framework to a classical system. Okay, but essentially from, I guess, 2016, it was proposed to use the same type of approach, hydrodynamical approach, to treat also 1D quantum system, where you know how to express J in terms of Q. Okay, so the charge in terms of the density, the current in terms of the density. And this is the case when you have essentially an integrable system like XXZ, which you can think as a sort of generalized free fermionic model at this stage. You have not to worry about the technicality. So the difference, there are two main differences between XXZ with interaction and XXZ without interaction, which is the free fermion model. So the first difference is that the spectrum is extremely more complicated because you might have bound states. So quasi-particles, they are not just free, but they can create bound state. But nevertheless, you know all of them. So you know all the masses of the bound, well, the masses, the energy of the bound states, and you know how to, for example, what is the single particle eigenvalue of any conserved charges on this bound state. So this is completely under control. What you also know is that the conserved charges, they have an expression in terms of this root density in the language of Bethe Ansatz. You can just think as a fermionic occupation number. So this is some quantity which is equivalent to n of k. So it's telling you how many bound state of type I have at a certain momentum lambda. If the system is a free fermionic, this is just the number of fermions, okay? Momentum k. If there are more particles, you have to sum over all the particles and give some root density for all of them. This specifies the state, the quantum state, like in the free fermionic model. This specifies the quantum state. It depends on x and t, where you are. The current, they have the same expression, but with the effective velocity of the quasi-particle. What I want to say is that beside any technicality, you can compute exactly, you know this V, you know this Q. This is given for you by the Bethe Ansatz. All right, so if you now, let's say, assume, as you should, that there is a continuity equation and that all the conserved charges, not only energy and particle number, they are transported inside this cone, well, then you have to write the continuity equation for all of those. So you sum over the index alpha. And what it boils down is just a continuity equation. If you see, you take time derivative here and space derivative here. What you get is a continuity, well, it's a Boltzmann equation, essentially. It's a continuity equation for the root density, which is what actually, if you have some boundary condition for rho, you can solve it. You can plug in here, and then you can get, as in the free fermionic case, a full expression for the conserved charges at position x and t, and the current at position x and t. So in particular, the magnetization also. Okay. Of course, solving this equation is very complicated because there are two main differences with respect to the fermionic case. So in the fermionic case, this equation is just this phase diagram that I was showing you, which you have every particle moves at a certain velocity, and then you just integrate over all of that. Okay, so this is more complicated because there are two reasons. The first reason is that they are infinite, because the number of bound states is normally infinite. So and the second reason is that even though it doesn't seem they are coupled, and the reason why they are coupled is that this velocity depends on the rho. So these are a set of nonlinear integral equations, essentially, when you write them. They are differential equations, as you see here, but when you have to solve it, it becomes a set of infinite nonlinear integral equations. So it's a very complicated problem to solve. But there is something happening here, and so this is the interpretation. I will not discuss that much, but there is something that particular is happening here that has to do with the initial state. So this initial state, this domain wall initial state in which you have all spin up from one side and down from the other side, is so special. Actually, this happens for any finite h, but in particular for that state, which is called a sort of representative state of this class, are so special that this nonlinear integral equation, you can solve it exactly. When I mean exactly, I mean you can write down a solution in terms of elementary function. The reason why you can do this, I will tell you in 1 second. So before, let me tell you a matter of notation which is important. So to solve the problem, you have to select certain values of the interaction in which the spectrum is under control. Otherwise, this is really impossible. And the value in which the spectrum is under control are the value in which delta you parameterize these ways. Cosine of gamma, and gamma is a pi of q over p. And q over p, capital P, they are coprime number. Okay? So that's some technical stuff, but you will see that it has some implication. Quite interesting, actually. But this you have to assume it for technical reason, because the Bethe Ansatz give you all the states, all the root density, only when this parameterization holds. Okay, so the reason why you can solve the problem is actually that among this infinite hierarchy of bound state, only 2 contributes for this initial state. That's the trick. Otherwise, it was impossible to solve anyway. So you can see that only 2 bound states, they contribute to the spin current. And their velocity, which is the difficult part, because the velocity, they are coupled. They depend on all the other bound states. That's a difficult part of technical difficult issue. Their velocity, they are actually very simple. They are the same as in the free fermionic model. So you do all this path to realize that the spin transport with interaction, it's effectively like in the free case, But the only difference is that what interaction does, in a very dramatic way actually, is to reduce the bandwidth of this fermion. So the allowed momenta for this for the part of the bound state which contributes, they only live in this interval now, minus pi over capital P and pi over capital P, where P is related to delta in this way. So essentially you are reducing the band for the fermions. The fermion, they cannot move now with any velocity from 0 to 1, like here. But their velocity gets somehow renormalized by the interaction, in a way. You can say that. So there is a maximum allowed velocity for the fermion to move due to the interaction. And this velocity is sine gamma, where gamma is again related to delta. So you see that if you take gamma equal to 0, so delta equal 1, which is the isotropic point, the particle they don't move at all. And that's why transport stopped to exist in a ballistic form at delta equal 1. Because the effective velocity of the quasi-particle, it goes to 0. And this is due to the interaction. There is no way. So this is the nice thing that you can already see from here. But then you can actually exactly get this profile, because it's like in a free fermionic model, but with the bandwidth of the fermion essentially gets renormalized by the interaction. There is this capital P which is related to delta. Okay, and you get some function which is an arc cosine again. So this is exact. You can check with the MRG. Of course, it's absolutely exact. And there is an interesting remark which I want to do. The remark has to do with the dependence on the interaction, which is very strange. Because, you see, you can also compute the spin current. This is easy, because once you know the magnetization, then you take the derivative use the continuity equation, you get the spin current. So this zeta 0 is some number. It's not very... okay, it's important, but it's some number, some coefficient. So what the remark that I want to do here, which is really surprising anyway, it has to do with prose and stuff about the Drude weight, but let me tell you, is the dependence on the interaction. So interaction, the parameterization of delta is cosine of pi q over p. So, and this is the parameter which you tune eventually in an experiment, hopefully. But so it's the parameter which controls the interaction. But you see that here it appears only p, which is the denominator of this fraction. So that means that this function is absolutely discontinuous in delta, because you can move delta by an infinitesimal amount by changing p arbitrarily, essentially. Okay? So this is like, in a way, a discontinued behavior for all the rational approximation of delta, if you want. But nevertheless, so it's a function that is nowhere continuous. But this follows from the exact solution. And you will see the numerics, how it deals with that. It's interesting also. Okay, so nevertheless, it's defined the continuation to irrational values. So if you take p goes to infinity, you keep fixed this value. This function is well defined, which means that essentially if you do an experiment, what you should measure is actually this value, not this value. Because I guess in an experiment, I suppose you have a finite. Okay, thank you. I'm 2 minutes and I'm finished. In an experiment, what you actually should, I suppose you have a finite width for uncertainty for delta, which means that you have to average, and this it's a set of measures 0, so you actually measure only this. But this I don't know. I mean, it's something that it can be interesting to. So the numerics, you can do it, of course. You can take delta irrational, so you can take this number irrational, and see then what happens. What happens is that actually the relaxation of the current to the irrational value which I showed before is very slow. It's extremely slow. You see that the there are these peaks here. Forget about these two curves, the average. There are these peaks. See, this delta is now, gamma is pi over the golden ratio. It's a famous irrational number, right? So you see that there are oscillation in the values of j. So it seems to relax to this value. Then it goes down here. Then it goes up here. Then it goes down here, etc. And these are the continuous fraction approximation of the golden ratio. So you see that there is this, and the limit exists. You see this is converging to the exact value, right? But it does in a very interesting fashion, I would say. All right, so let me briefly say that there is no Tracy-Widom when you had interaction. So if you know the story, it's interesting. If you don't know the story, I just tell you. There is no more Tracy-Widom. There is no more Airy function here. There is a function which the scaling variable is now x minus t sine gamma over t to the 1/2, which suggests this is the scaling. So you see this is completely different from at the edge, from delta equals 0 to delta different from 0, which is suggesting that actually the right is continuous. The scaling variable depends in a continuous way from gamma now. So if you take gamma equal to 0, you are going toward the isotropic Heisenberg point. You should expect pure diffusion and now super diffusion. So that's the conclusion. Well, let's say it's the, one of the main conclusions of this work. So numerics tells you that you should probably find super diffusion, but probably is not. It's just pure diffusion. So the transport is ballistic up to delta equal 1, and then it becomes diffusive. This was also pointed out recently by Jean-Marie Stéphane and other people from Saclay. All right, the last final thing. There is a way also to compute the Drude weight from the exact solution that we have. The Drude weight is the coefficient of the delta function in the Kubo formula for the conductivity. You can use a formula by Lievsky, was a student of Prosen and Denardis, to compute the Drude weight once you know the spin current for the domain wall initial state, for example. So the result is the exact bound found by Prosen. So this is a way also to verify that. So Prosen and Iliesky, in a paper of 2013, they prove actually that the Drude weight for the spin current in infinite temperature for this type of setup has to be larger or equal than something as a lower bound. Okay? Here we prove that the lower bound is saturated because we can exactly compute the Drude weight and show that it's the lower bound found by Prosen. So the bound is tight. I don't know, if you don't know the story, it was also an interesting observation. So these are my conclusions. The most important, I guess, is that we can solve exactly this problem of spin, transport in the XXZ spin chain from this class of state. We find that delta equal 1 a behavior which seems to indicate pure diffusion, no more super diffusion. And okay, there are many things interesting. So the profile of the magnetization, which has this, quite unusual, let's say, dependence on the interaction. But nevertheless, you can continue to irrational values. And then we prove the tightness of Prosen and Iliesky bound for the Kubo formula for this model. So thank you very much for the